Hi everyone, my name is Eric. I'm in the Exascale Lab group, headed by Dr. Barbara Chapman. And my research is on task-based programming. On the left here, I show an example of how we typically write parallel programs today. You have a set of work. Here I use for hooks as an example, and you parallelize the individual sections of work. And at the end of each region, there is a synchronization point where you wait for all the previous work to complete. This style of programming works well for very regular applications, but sometimes you have irregular computations, like say sparse linear algebra is one example, sparse matrix. And your execution starts to look like this, where of these loop iterations, maybe one takes a really long time and then the others are shorter. And then there's a lot of time that the other processes spend waiting for the first one to complete. And this equals a lot of wasted time because of these loop iterators here. So the alternative is, an emerging alternative is task parallelism. And the goal in a nutshell of task parallelism is to make the execution look more like this, where when a process is done, even if it's cohort of processes doing the first set of work isn't done, it can take tasks from the next work group and start working on them. And the goal is to eliminate idle time, which is of course good, but it's not always that easy. Obviously, writing a runtime that can distribute work like this is a challenge. There's also a challenge for programmers who write task-based applications, like load balancing versus locality. If you move around tasks or make the task size more granular, you can make more use of the idle time and have better load balancing, but there's additional overheads from the scheduler, and you lose locality as you move tasks around either within a node between cores. You may lose cache locality, or if you're going in a distributed setup, you may have to transmit data over the network, which is not good. And also the alternative is how to, as a programmer, you can write a program intuitively that as a set of tasks. So my research is sponsored by the energy company, Total Energies, and they are interested in task-based programming for a variety of applications they have. This image here is the one I'm working on right now. It's called reverse time migration, and it's a method of imaging subsurface, like for example, looking for oil. And it's very computation intensive, and but it's also very input-output intensive. So, for example, I believe the cost is often dominated by input-output reading wave fields to and from disk. And one of the goals of task-based parallelism is to seamlessly overlap the reading of data from the disk and the computation on the GPUs, and we've already had some success with that. So we're taking kernels that do seismic imaging applications and have ported them to CPUs and GPUs and looked at how we can use tasks to and comparing them to traditional approaches. I think that's all I have to say. Thank you. I'll take any questions.
Those different tasks are synchronized with each other.
In my case, there's because the application, the computational part of the application is a stencil. Each task has to synchronize with its neighbors, and at the end of the time step, the ghost region, it's called, where you're trying to access points from the neighboring block have to be transferred over. If you write this using MPI, you have to do it manually. The goal of distributed task-based framework would be to do it automatically, figure out what needs to be transferred and do that. Yeah, so one of the challenges here is representing the dependencies between different tasks. For example, the dependency between the computational step and the input-output step, which takes the wave field and transfers it to disk, and then from the pass. Hope that answered your question.
Yeah, so along those lines, do you think the compiler would be able to do enough analysis to, let's say, between your work group 2 and work group 3 figure out those dependencies, say for this stencil shape?
What I found in practice, from various things I've read is that, for, with OpenMP, that it's, often difficult for the compiler to optimize between steps like this, because there is the barrier here. I haven't really seen any compilers have, success with, sort of inter-procedure
Yeah,
optimization between the multiple steps, but, that would be another interesting angle to look at.
So how would you go about in practice composing optimal sort of task parallelism program? I mean, that model there on the right hand side, how would you write code that would run like that?
Yeah, so what I've been doing is taking the domain. The domain is like a cubic domain in this example, because it's the represents the Earth, and splitting into chunks. And in one experiment we tried different chunks, different ways of splitting up the domain among the different tasks. So for example, making all the cuts in the X dimension, or some in the X, some in the Y, and we found a really large difference in performance between them. Never really looked at that deeper to understand why there was the huge difference, but so we split the domain into chunks, so that each chunk becomes a task, and the task, because of the stencil shape, each task depends on its neighbors from the previous time step, but all of the tasks within a time step can run at the same time.